Hi. This is the second recording. As you can see, I have solved it already. That took 6 minutes, but then it turned out that I had put another source of sound than my microphone, so that there was no sound to the recording. So I'll just make a recording where I explain this, what I did here. In the first question, we may assume that we have proven that the z function of any affine variety has this form, that is, it's a power series with integer coefficients starting with 1. I wrote it like this. That's maybe not the best form. T to ith, where we start with 1. And now we're talking about any projective variety. We know that it has a finite radius of convergence, but that's not relevant here. We should prove that if this holds for any affine variety, then it will hold for a projective as well. In problem 7, we wrote the projective space as a direct sum of affine spaces with subsequent lower dimension. And in each of these, we have an affine variety, because it's the sum of affine spaces, and the equation is generated, or the equations are generated by the given equations. Say if we have this as a complex, a projective variety, a 3D, then we first take the affine x squared plus y squared equals unity, and x plus y equals minus 1. And then next we take the curve at infinity, x squared plus y squared equals naught, and x plus y equals naught, and etc. So this way we write it as a sum of as a discrete junction of isn't it a conjunction of affine varieties? And then the total number of points is given by the number of points of the lower dimensional varieties and the affine one. So the z function of the projective variety will be a product of z functions for the affine varieties, and they have all this form, so the product will as well. I think I made this a little too complicated. I hope you were able to follow it. Next, we may assume that that we have shown it if the variety is given by a single equation, then it should hold for any equation. And here we have a variety given by two equations. This one having the z function z1 and this z2. We need to find an expression for the z function of the intersection of the two ones. The number of points in q to the rth of the intersection, there should be an intersection sign, we get by taking the number of points of this guy plus the number of points of this guy minus the union. And the union is given by the product of the two. Similar formulas can be made by 3 or more. Or we could make a proof by induction. I think it's easier really to make a proof by induction than writing up the general function for an intersection of n varieties. So just make a proof by induction. And then we have the z functions, these two multiplied and then divided by this, but 1 divided by this is also 1 plus some power series with integer coefficients. That detail I missed in my first recording. So the product will be a power series of the same kind. That's it. So it need only to be proven by an affine variety defined by one equation.